Check that it works. Maybe he can help.
Yes.
Okay.
And,
Now it works. Yeah. Okay. So this is a calculation that was actually born in Florence.
thank you,
Please
Lorenzo.
go ahead.
Thank you, Lorenzo. And also, I would like to thank the organizers for this opportunity. And it's nice to be back in CGI, also in Florence, where I started my postdoctoral career. Okay, today I will talk about collinear contributions to QCD resummations for hard scattering observables. This work has been completed in collaboration with Stefano Catani. Okay, so I also realized that when you talk towards the end of the conference, all the introduction has been given. And for me, like I will quickly go over fixed order contributions and why we need resummation. And in the context of resummation, I will talk about transverse momentum resummation and its various components. Then I will go over our computation for the one such components which controls collinear degrees of freedom and present results up to next to leading order. And finally, I will summarize. Okay, so let's consider a hydroproduction of a system of final states denoted by F and its invariant mass M. And to have a theory predictions for this process, we depend on the pattern model where the long range, the long distance physics is factorized from the short distance physics. And here the long distance physics is given by the pattern distribution functions, and we obtain or we extract them from the experimental data. And the pattonic cross sections we can, in fixed order perturbation theory, we can expand in the series in powers of strong coupling, and then we compute order by order. Now we can ask at this point, we can ask this question whether fixed order contributions is sufficient. In that case, we can look at the structure of fixed order contributions, and already we have seen many talks. So if we look at the contributions coming from fixed order, we can separate into two parts. And what we can say, one is regular in the limit. Here I'm talking about QT distribution. So in the limit QT, small QT limit or QT goes to 0 limit, and then other contributions are basically singular when QT goes to 0. However, the good news is that these kind of contributions are of infrared, basically soft and collinear origin. So they have some degree of universality, and that leads to resummation of these terms. Now, here I want to show, what resummation does. So, so here I have taken a plot from paper by Massimiliano and Stefano, where you can see that if you look at the dashed lines denoting fixed order contributions to the neutral Drelian production, and if you look at the solid lines denoting the resummed contribution, you will see that in the low transverse momentum region. So while resummed predictions provides a smooth curve or smooth result, however, in the fixed order case, it diverges. So quantitatively, if you want to understand what happens, that let's at a relative order n compared to the leading order, we see these series of logs. And then, since usually we do, and also it is easier to understand in resummation in the impact parameter conjugate to QT space. So we can kind of regroup these logs into some kind of perturbation series, and those are basically depending upon the logarithmic terms that you consider. You can tell that whether you are looking at leading logarithmic accuracy, you are doing resummation of leading logarithmic accuracy or next to leading log or so on. Now also, I mean, to compare with data, we can also look at how resummed prediction also helps us to compare with data in better way. So here I have again I'm considering a neutral trillion, but in this case here like there are the contributions are next to leading order plus next to leading log accuracy, as well as the higher one N3LO plus M3LL. So we find that okay, bulk of the events are produced in the low transverse momentum region, and we also find our theory is consistent with data. And this kind of improved predictions, we know that will help us, for example, in the case of determination of the mass of the W version. So the transverse momentum distribution of the W version is very important. So I mean, already Alessandro has talked about it, and also if we have improved predictions including fixed order as well as resummation, then we get a better prediction throughout the entire region of phase space, and which will also help us to study other standard model parameters. Now, how are these large logarithms we are talking about are resummed? Well, it is given by the transverse momentum resummation formula. And if you see, we have here the sigma 0 denotes the leading order contribution, and here S denotes Surakov's soft contribution, and we have again pattern distribution functions, and then we have something called hard collinear factor. And if we look at the structure of hard collinear factor, we see that okay, so we have this H function, and here I have given for the gluon channel. For quark anti-quark, you can just forget about this Lorentz indices, and there will be again 2C function corresponding to quarks. So here as you can see, I mean, when I started about the singular contributions, I told about that since they are of infrared origin, so they have some degrees of universality. As you can see that in the hard collinear factor, there is a hard function which contains mostly contributions coming from virtual origin, and there are two collinear functions, and as you can see, they don't depend on F, which is basically process. And in this talk, I will be mostly focused on computing these collinear functions for both gluonic channel as well as quark anti-quark channel. Now, coming back to gluonic channel, since it has a tensor structure, we can separate, or we can further write these collinear contributions to two separate contribution. One is called azimuthal independent part, and other is called azimuthal dependent part, where basically this azimuthal dependency is of the azimuthal angle of the transverse momentum. Now, there are a lot of progress in computing these collinear functions, and as you can see, for the coefficient function C, which controls the azimuthal independent part, they are now known up to third order in perturbation theory. The coefficient function G, which controls azimuthal dependent or the correlation part, they are known up to next to leading order. And you can imagine also, since here these computations that I gave, it's kind of in the production channel, but you can think of similar collinear functions in the decay or in the final state, and they are called time-like collinear functions or fragmenting jet functions. Now, okay, they are known, but in our work we recomputed them, and we using our formalism, and there are important differences, and I would like to talk about that. Okay, here is the workflow for our computation. So we started, since we are interested in computing the collinear contributions, then we start with a collinear factorization of matrix square matrix element. And in the collinear limit, we know that the matrix element square or matrix element, but we are interested in the matrix element square, factorizes to a singular contribution which contains the divergent singular behavior in the collinear limit, and we will have a reduced matrix element. Then once we have these splitting kernels, we can our plan is to first integrate over all the independent radiation, but keeping the sum fixed, so that like our this and doing that we get the differential collinear functions. And I mean, getting this differential collinear function, our intention is that once we have this, that means all the observables that depend on the total radiation that can be computed from starting with our differential collinear functions. Then once we have differential collinear functions, we again, I mean, we take actually two such variables here. Mainly, I will discuss about transverse momentum case distribution, but also we compute the zero jettiness variable. And for the transverse momentum distribution, we have in the literature there is a subtlety about rapidity divergences, that once when you compute these individual functions, you get rapidity divergences. But in our case, we do not have rapidity divergence, simply because we use the auxiliary vector which we define, or which used to define the collinear direction. We, instead of taking them light-like, we take them time-like. Okay, so now let us discuss a bit about collinear factorization. So I mean, if you look at the soft factorization, so you will see that in the soft factorization case, the current factorizes, but it depends upon the hard patterns. I mean, those which are not soft, as well as it depends upon the color of the hard patterns. However, collinear factorization is more universal. So if you look at the collinear factorization, what happens? This collinear splitting kernel, it depends only on the momenta or quantum numbers of the particles that are involved in the collinear splittings. However, in general, this is not true. Like soft factorization, you can have also dependency coming from the non-collinear patterns, and this is a kind of a quantum effect. You can think of like this effect comes from the loop, and or also like I mean, you can think of like a soft gluon, soft wide angle gluon, actually in a loop, which basically correlate a collinear pattern to non-collinear patterns. So to this end, we can actually define two regions. So one is called time-like region. So time-like region, here I define, let's understand that all the collinear particles are in the final state. So the process is, you can imagine like this. And in this time-like collinear region, the splitting kernel is process independent, which means that this splitting kernel that I'm talking about is depends only on the momenta and the quantum numbers of the collinear particles. But there is another region which is we can define space-like collinear region. So imagine that there are collinear particles both in the final state as well as in the initial state. And in this case, this strict collinear factorization is violated, and it will have also it has some interesting aspect with the pattern model also, it will have impact. Now, since I talked about in my workflow, I talked about that taking auxiliary vector to time-like, I would like to comment on the dependency or maybe functional form of the splitting kernel on the auxiliary vector. So apart from the dependency on spin and color indices, the functional form of splitting kernel, that P, depends also the sub energies and then ratio of the momentum fraction. So people generally calculate this is splitting kernel using a light-like auxiliary vector, but you can one can also set once you have splitting kernel, one can directly set n squared to non-zero, and by doing that, you are basically adding some transverse component to this auxiliary vector. And since you are interested in the leading power of collinear limit, and those transverse momentum contribution basically are subdominant, and they can be neglected. So with this, now I can actually go on to define differential collinear functions, and as you can see, and this for the time-like region. That means my splitting kernel does not have any dependency on the non-collinear patterns. So I just what we do, we integrate the splitting kernel over all the radiations, and keeping the sum fixed. So and for the space-like case, you have to just imagine that instead of not having the dependency on the non-collinear patterns, we will have the dependency. So, and this dependency is basically coming from the splitting kernel itself. For the time-like case, splitting kernels are known up to third order in perturbation theory. However, for the space-like case, since it depends upon the non-collinear patterns, they are not fully known up to third order in perturbation theory. So once we have differential collinear functions, we can go on to define collinear functions for the transverse momentum case. So we start with the differential collinear function, and then this is the observable definition we put. And then we also simplify, since we are taking this matrix element in the collinear limit, we simplify the phase space in the collinear limit. And here again, I have given for the gluonic channel, but for the quartz channel, we don't have this structure. Instead, we have only kind of azimuthal independent contributions. Now going from time-like to space-like, we again add a dependency on the non-collinear patterns, and we follow the similar procedure. This is the observable that we are interested in, and then we simplify the phase space in the collinear limit. Now, kind of we have set up our formalism, and now and in the most general way, that keeping all the dependency non-collinear pattern dependency in case of space-like. However, people have seen that if you are in and in this work, we are actually computing up to and then next to leading order. If you are doing your calculation up to next to leading order, this dependency for the space-like case, the dependency is not there. So these collinear functions are basically like the space-like collinear functions are like time-like collinear functions. But this dependency will start actually at M3LO. But in this case, we are only computing up to next to leading order. So as I told you that if we, since we have our differential collinear functions, so we can also define this beam functions for the zero jettiness case, and again, we start with our differential collinear functions, and we use the definition for the zero jettiness, and then we simplify our phase space, which is same both for transverse momentum as well as zero jettiness. Now, at this point, I would like to also comment that some definitions coming from soft collinear effective theory. So, in general, they are way of defining these collinear functions is similar to our way, except two differences. One is with respect to using light-like auxiliary vector and time-like auxiliary vector. And in other point is that for the space-like region, their way of defining collinear function is completely process-independent way. However, our definition keeps this process dependency intact, which comes from the collinear splitting kernel. And with respect to this, using this light-like and time-like auxiliary vector, in the next slide, I will talk about this rapidity divergences, which comes in the transverse momentum dependent functions. So in general, if we want to compute order by order in perturbation theory, the QT differential distributions for any values of QT, then it can be done, and one can then just kind of extract the singular QT behavior from that computation. And this actually Massimiliano and Stefano, they did 15 years ago. They just extracted these collinear functions from the computation of QT differential. However, if we are interested to compute these singular elements such as soft functions or collinear functions individually, so what is the procedure we follow? We simplify our matrix element calculation in that limit as well as phase space in that limit. So that means this divergence actually comes from that. So rapid divergences are artifact of a priori approximation that we made both to the matrix element as well as the phase space. So here I have shown that here we are doing the phase space approximation in the collinear limit, and here we are starting with the matrix element in the collinear limit. And by doing so, we are actually taking the minus component of this total radiation to infinite, and it should be the collinear, for the collinear region, the plus component should be greater than the minus component. However, it goes to infinity, but still it is okay if the differential collinear function is well behaved in the k minus goes to infinity. However, it is not the case, and you get this k minus goes to infinite limit, you get some divergences, and people generally use rapidity regulators to kind of do the calculation and then take the limit in the end. However, in our computation, since we have this n, which is time-like, this actually saves us, and we don't have rapid divergences in our calculation. And here is an example how it happens, and here it is at alpha s order. So let's look at this term, which comes from the real contribution to Alderelli-Paris evolution kernel. So this term, if you using the kinematics, we get in this way. So now if you set n square equal to 0, there is no way you can regularize this endpoint divergences. However, if you keep n square non-zero, okay, it can be space-like or time-like, but in our case, we are taking it as time-like. If you keep it, then you can regularize it, and then you get log of this n square qt square, and then you get some terms, relative terms. But since you are interested in the leading power, again, you can forget about when qt goes to 0 limit. Okay, now with all this subtlety, now we could present bare results for both differential collinear functions and also at the integrated level. And for the presentation purpose, I will only at the bare level, I will only talk about the space-like case, and then finally, when presenting the final result, I can also present the time-like results. So here we first, do the expansion. So this differential collinear functions coming from single radiation, and we have a double radiation, and then one loop to one single radiation. Okay, so this is at order alpha s. This is the structure here. This P denotes the real contribution to ultra-rarely Parisi, and then we have for the azimuthal correlation or dependent part, we have this contributions to for the GG and for GQ or GQ bar. And then we, using the previous formulae, we integrate and then we get in the transverse momentum space. And then once we have these results, then we use this Fourier transformation to go to the impact parameter B space. So once we have results in the impact parameter space, we use this IR factorization. So what we did, first we remove ultraviolet divergences using a renormalization of strong coupling. And for simplicity, we have set all the scales here to both renormalization and factorization scale to B naught square over B square. So once we remove ultraviolet divergences, the remaining infrared divergences, first we remove the initial state collinear divergences through this mass renormalization, and then what remains, we factorize to this two renormalization factor for quark and gluon. And also notice that this renormalization factor is same for both azimuthal independent as well as azimuthal correlation case. And also, I would like to point out one thing, that this renormalization factor you get, it contains all the divergences, infrared divergences. Similarly, when you compute the soft, you will get a this kind of factor, renormalization factor. And also, we have virtual corrections. We can write some renormalization factor times some finite. So all this renormalization factor basically cancels, all the poles cancel, and the factorization formula I started with, you get Sudakov short function and the finite contribution to the hard function. Okay, so now I can show some results. So alpha s, we obtain both space-like results, and they are known. And at alpha s square, we obtained for the azimuthal correlation case, we obtained the space-like regions, and this result is also known, and but we are in agreement. And time-like case also the results are known, and we are in agreement. So with this, I can go to summary. So okay, so fixed order predictions can be plagued with the large logs stemming from soft and collinear origin. And for better theory prediction, we know that we need to do resummation for small values of observable, and then and we saw that with the collinear case, we can actually compute these coefficient functions starting with the collinear limit or soft limit if we are interested in the soft function. And these computations or these collinear functions and the singular this renormalized constants are important. For example, for QT slicing and some this various algorithms which aim to compute these differential functions, differential cross sections. Okay, I presented our method to compute both space-like and time-like collinear functions using respective splitting kernels. And to compute these functions, we first defined a differential collinear function, and then we integrate using the observable we are interested in. And I showed for both QT as well as zero jettiness. For the azimuthal correlation, I showed the result up to N and LO, and the azimuthal part I just showed up to NLO, and actually we are finishing for the NLO case. And we stress that the space collinear functions can be process dependent, and this dependency is basically coming from the process dependency of splitting kernel. And another important point that we so I showed that we used time-like vector so that we don't have rapid divergences in our problem at all. And with this, I thank you for your attention.
Thank you, Prasanna. Questions or comments? Einan.
Thank you very much for the interesting talk. So if you take the n squared to 0, right, then you should get back the rapidity divergences, right? And so have you checked that in this limit, so the dependence on n squared is controlled by rapidity anomalous dimension? What is the dependence on that n squared?
Okay, I mean, okay, if you have n squared, okay, first thing, this n squared dependency at the end should cancel, because like we are using a regulator. Actually, in this in the computation of splitting kernel, people use this n as also axial gauge vector. So it's the same for axial gauge and the auxiliary vector. And if we use once we compute, we have n square dependency through logarithmic, and then if we multiply both collinear functions, they cancel, and you get back to actual logs m square over qt square. Now, if you have if you want to take a limit n square goes to 0, and then see this whether they are governed by the anomalous dimension, that I have not checked. But instead, to start with the at the differential level, differential collinear function level, setting n square equal to 0, and try using also some of the lab regulators that are available, I could kind of reproduce the results at NLO like people did.
Okay, thank you.
But I'm sure that this is governed by this rapid anomalous dimension.
Massimiliano.
So I have maybe I should know it, but now I'm a bit confused. So in our old, if you want, old-fashioned approach, we have this. So as you said, we have computed this coefficient somehow indirectly up to second order, and the soft terms are basically just a constant into the into the definition of the hard coefficient. Okay, so now you have this this approach in which you avoid basically rapidity divergences this regulator. So what is the soft counterpart in this?
You will again the same constant. You will not have any dependency on n. You can show, if you are looking at a massless QCD, you can show that just dimensional analysis. You can show that, like, for example, soft, you need to have this P1 goes to the scale. If it scales, it should be cancelled, and P2, those kind of, if you use that, you can show that there should not be any n square dependence on the soft case. So it's exactly the one you are having just a constant like the other case.
But then when you renormalize, when you define renormalized infra-renormalized quantities, there is always I mean, a constant that is sort of I mean, has to be fixed, you know. So this is it will be basically equivalent to to what we call the resummation scheme dependence.
Exactly.
Okay, it will flip from one piece to the other depending on how.
Here also, I mean, I did not discuss about this scheme, hard scheme and minimal scheme to define this constant, but we define that. For example, I mean, this Z that we define, depending upon the scheme, it can have a constant or
Okay.
constant. That, yeah, so we are defining in hard scheme. So that in
Okay.
C there is no delta 1 minus Z terms.
Okay.
Exactly the same way.
Thanks.
Maybe it was even written on this and I missed it. If you go to slide 19, where you started to present some of the long results, at some point there was a delta, small delta parameter. I think in the previous here.
No, this delta parameter is basically like
Sorry,
epsilon.
I
You can
couldn't
think
see
of
it.
like
Sorry
it's just
about
a
that.
Fourier transformation,
Fine.
like for any.
I just couldn't read it, so I was a bit.
Delta can be any n epsilon.
It's written. Fine.
Yeah.
I thought that there was something subtle, but no. Okay, it's just I cannot read that far.
Yeah, actually, I said perhaps in line with what Einan was saying, rapidity divergences in some sense they are bad, but in some sense they are good in many cases because you can then get an evolution equation, right? Maybe which would not be useful in this context, but so I am guessing that here maybe such an evolution equation would be replaced by taking derivatives with respect to n.
Yes.
Which is actually quite interesting because this is the way that evolution, the Sudakov evolution equations were derived, 35 years ago as derivatives with respect to the gauge vector.
Yes.
Is this does it resonate? You think this is the case?
Yes.
Okay. Yeah. Actually, I had never thought of this. This is very interesting, actually. Very well. So let's then thank Prasanna again. And I remind you, you got an email. The schedule has changed. We reconvene at 2 o'clock for the talks by Tanya and Zheng Rang, so that people can then take trains and do things that they have to do. See you later then. Thank you very much.